Okay, the promised screencast for our holiday homework comes from Chapter 13, which is grandly entitled Discrete Probability Distributions and Simulation. So we're firstly going to just look at probability distributions, and I'm going to say that what we need to do here is we need to define what a random variable is. So we say we usually let x equal a random variable. Now the word discrete just means that it can take on it's discrete, meaning it's just a whole number, so a countable number, discrete random variable. So they're going to be whole numbers. Nice. So we define x as a random variable, meaning that it can take on any whole number, that it can take on any whole number. Okay, that's a nice general start. X is a random variable. Now that x, that can be defined as whatever, depending on the question. Let's get started. I'm going to say x is, I'm going to flip a coin 4 times. Let's have a look at an example. Flip a coin 4 times and observe the number of heads. So in this example, then we're going to let x, which is the random variable, equal the number of heads. Now you just saw that come up on my screen. I'm just going to pause and plug in here. Okay, we're back on the air now. I've plugged my machine in, although my writing might get even worse now because I have to tilt my screen at a strange angle. Anyway, with those excuses out in the open, I have defined x as the number of heads. So what we do now is the number of heads is going to be represented in it. So we're going to construct a little table here where lowercase x is going to represent the individual possible values for our random variable. So when we flip a coin 4 times, what are the possibilities for the number of heads? Well, hopefully you realize that we can have no heads. We can have 1 head. We can have 2. We can also have 3. And we can have 4 heads. So they're the possibilities. Now what we do here in the bottom row is we list the probabilities. So we say the probability that the random variable equals 0. So what is the probability of 0 heads? That goes in there. Now the probability of 0 heads in 4 flips of a coin is 1 half by 1 half by 1 half by 1 half, or 1 over 16, which is 1 over 16. Now when we look at the probability of 1 head, then we've got to not just consider still a half by half by half by half, but there's 4 positions that head can sit in, so it's 4 over 16. And when we look at 2 heads and 2 tails, then there are actually we need different configurations of that as well. So we can have head, head, tail, tail, we can have head, tail, head, tail, and there are actually 6 configurations of that. And for those of you that are interested, that 6 comes from 4C2. 4C2, nice little link in with the last section. This is 4C1. There's 4C1 ways of coming up with 1. This is going to be really interesting for us, something that we're going to use a bit more of, so make note of that. 4C3, this will be 4 over 16, and then back to 1 over 16 here. If you add up 1 16th, 4 16ths, 11 16ths, 4 16ths, and 1 16th, then you'll notice that that sums to 1, and that is a probability distribution, ladies and gentlemen. That's all the possibilities, so it has to sum to 1. We can have 0, 1, 2, 3, or 4 heads. So that's an example of a probability distribution table. Okay, let's have a look at an example, say from exercise 13A, which I'd like you to be doing as soon as you've gone through this screencast. I'd like to do an example for you just to help out in case you're going to get stuck. Exercise 13A, we're going to go to page, what would be sensible here? Page 371. and we'll have a look at question 9. Okay, so in question 9, when a pair of dice is rolled, 36 equally likely outcomes are possible. Let y denote the sum of the dice. So our random variable y is equal to the sum of the dice. Now the dice have been rolled twice. What are our possibilities for the sum? Can we have 0? No, we can't. Can we have 1? No, we're rolling 2 six-sided dice. We can't get 1. 2 is our lowest. So into the table we're going to have a lowercase y representing the different values of our random variable, which start at 2, and we can have sums now going up to 12. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right, now we're going to find the probabilities for each of those. So what's the probability of rolling a double 1 and getting 2 as a sum? So, this is what we're doing. We've got 2 dice, and we're rolling them out, and we're looking at the probabilities of, in this case, a double 1. So a 1 here on this one. What are you doing? And then the same over here on this die. We've got a 1 there. We've got a double 1. Well, there's one. That's a 1 in 36. I thought you'd appreciate a nice little diagram there. That's a 1 in 36 probability, isn't it, of rolling a sum of 2. What's the probability of a sum of 3? So for a 3, this is going to get complicated. That's a 1 or a 2 or a 2 or a 1. So that is 2 chances in 36. I'm going to keep everything over 36 so that my numerators should sum to 36. Now 4, the sum of 4, that's going to be, that's a 1, 3, that's 1, 3, that's 2, 2, that's 3, 1. Can you think of any others? That's 3 in 36. A 5, we can get a 5 by rolling a 1 and a 4, a 2 and a 3, a 3 and a 2, a 4 and a 1. It's 4 in 36. Is it really just going to go up by 1s each time? A 6. We can go 1, 5, 2, 4, 3, 3, 4, 2, 5, 1, 1, 2, 3, 4, 5 in 36. A 7, a 1 and a 6, a 2 and a 5, a 3 and a 4, 4 and a 3, a 5 and a 2, a 6 and a 1, 1, 2, 3, 4, 5, 6 in 36. 1, 2, 3, 4, 5, 6. An 8, well, we can't roll a 1 anymore. It's going to give me a 2, a 6, a 3, a 5, a 4, a 4, a 5, a 3, a 6, a 2. 1, 2, 3, 4, 5. We're going to go back down. I'm going to guess back down to 1. 5, 4, 3, 2, 1. Do you reckon I'm right? 1, 3, 6, 10, 15, 21, 26, 30, 33, 35, 36 over 36. Beautiful. There's my probability distribution. So then we can go and answer the questions. 9a says, what are the possible values of the random variable y? We've answered that, 2 to 12. Find the probability y equals 7. We've done that. There it is there, 6 over 36. Determine the probability distribution of the random variable y. We've done it. We did all that without even being asked to, because we love it so much. Okay, I'm going to leave it there. I'd like you to do exercise 13a on the back of this, and actually I think you can do 13b as well. 13b is very similar to 12c and 12d, just using some combination factorial sort of notation, and you can see the example on page 374. So I'm going to leave you now to do exercise 13a and exercise 13b from the work requirements. From work requirements, I'm going to put another YouTube together for 13c. See you later.